Hi, John Chamberlain here with Fundamentals of Light and Laser, Course 1. Today we're going to look at Laboratory 1-4A, Prisms and Lenses. Okay, so let's look at some of the equipment we're going to be using for the first part of this lab. We're going to be using our prisms and our laser beam. We're going to be using our laser level because it puts out a nice flat beam of light that shows up really nice on going through our prisms. And we have our beam block, which we'll use as our screen over here on the edge. And we have our nice projector here that we'll be using that will help you look over my shoulder and you'll be able to see things from the top-down view. So let's get started and shine that light through those prisms. All right, we have taped down our laser level, and you can see our beam going across the paper. And we're going to move our prism into the beam, and you'll see it as it refracts through the prism. As we change the angle, you'll notice that the refracted beam has a different angle of deviation. The goal for this part of the activity is to find that minimum angle of deviation. Okay, from this angle you can see the beam, incident beam, striking the projection screen. And when I move the prism into place, you can see the deviated beam being refracted through the prism and striking the projection screen over here. And what the purpose of this lab is to note that as we rotate the angle of incidence, that the deviation of that refracted beam varies from going far back to a minimum. There's about the minimum right there, and back to the maximum again. And so we're trying to locate that minimum point. So I'm going to say the minimum is right about there. Okay, so now we're going to trace the outline of the prism so that we'll know where our boundaries are. And then Derek can trace the incoming ray by putting some dots on the paper to reflect the, and we'll come back later and connect those dots. Okay, so Derek, now you can move that prism off of the paper, and we'll start off by verifying the angle of the prism, the apex there, what the book calls angle A, and looks like sure enough, as we expected, it's 30, 40, 50, 60 degrees. Okay, so we'll note that angle A is 60 degrees. Now we need to draw the lines that connect the dots for our incident ray. Very good. And the refracted ray as it goes through the prism. And then finally the deviated beam as it exits the prism. And now the purpose for this lab is to measure that angle of deviation. Now that angle of deviation is going to be the angle that the deviated beam makes with the incident beam. So can you extend that line for us back, all the way back to that incident? Carefully draw that line all the way back to the, so we can find that point of intersection, and then we'll place the protractor right so that the vertex is right on that point of intersection. And now let's measure that angle at 0, 10, 20, 30, and what do we have there, Derek?
We have 35, 36, right about 37 degrees.
37 degrees. So our angle of deviation is 37 degrees for delta. So now, okay, real quickly we can do the calculations for this lab. As we saw the ray coming in to our 60 degree prism, and had an angle of deviation, a minimum angle of 37 degrees. We can put that into our formula that says the sine of the sum of the angle of our prism plus the minimum angle of deviation divided by 2, divided by the sine of that angle of the prism divided by 2. So that would be 60 plus 37 divided by 2, and the sine of just 60 divided by 2 comes out to an index of refraction calculation of 1.498, or very, very close to 1.5, which is probably what the index of refraction is for this prism. All right, the next part of this lab asks you to examine total internal reflection. So let's go and do that next. Okay, Derek, tell us about total internal reflection.
All right. As we use a 45, 90 degree prism, we'll notice that unlike the equilateral triangle, when we put it into the beam, into the incident beam, we'll notice that the beam comes in here, hits the back here, goes down, hits this back here, and goes straight back out along parallel to the incident beam. And as I showed you when I was lining this up, they remain parallel even though I move up and down. They stay parallel to each other, to the incident beam. Let's talk a little bit about retroreflection. Retroreflection is when the incident beam hits two prisms and the beam path is altered so that the exit beam and our incident beam are parallel to each other. So let's put our first prism in position here. And this is similar to the way that they use periscopes. So now that we've got this one down, we're putting it down here. And now, when we position our second prism, now we have our exit beam becoming parallel with our incident beam.
For the last part of Lab 1-4A, we're going to measure the focal length of a convex lens. To do that, we've got two laser pointers set up, aligned with parallel beams. We can tell they're parallel because they're producing 2 points right up close, and if we move the beam far away, they're also producing the same spacing, and so we're pretty confident that the spacing is parallel all the way along this distance. We've got our convex lens set up in a lens chuck assembly, and we don't have the same full-size 3-inch lens that we would like to have, but this one's just enough where we can get the spacing of our beams to reach the edge of our lens, and you can see the spacing of our beams is now diverging, but if we bring it closer and closer to the focal point, we do find that they converge to a point. And now we're able to use our ruler and measure the distance between our focused image and the center of the lens, and we find the distance to be approximately 5.8 centimeters to the distance to the center of our lens. So that is our measurement for our focal length for this convex lens. Okay, we have another convex lens. Let's just, because we can, let's put it in there, see if it's got the same focal length. And you can see that it diverges. And here its focal length, oh, it's quite a bit farther away from the other than the other one. And we can place it and measure its distance. And it comes out to approximately 22.8 centimeters. So it's got a considerably different focal length from the first convex lens we measured. So all convex lenses are not created equal. All right, the lab asks you to additionally consider a concave lens in addition to a convex lens. That would be a diverging lens, and we have one diverging lens here, and it's a little harder to imagine how that would work. If you place that in the path of these parallel beams, we get a we cannot get a focused beam. In fact, we just get a greater and greater diverging beam, as you can see. And so the text asks you, well, how can you find the focal length of a diverging lens like this? And if you'll look at your text, you'll see that what you have to do is to trace those rays back behind the lens to find where they would have crossed each other had they existed back on the other side of the lens. It's kind of hard to describe in words. And so you can be as clever as you would like. One way I might consider doing it would be to imagine if I could place my ruler along that edge of that beam, right where it comes out and diverges. I could imagine this top ray going all the way back through the lens and back on the other side of my lens on that side. And similarly on the bottom part of the beam, if I could imagine that part going back up all the way to through the lens, and where those two rays cross back here someplace, looks like about maybe 2.5 or 3 centimeters, that would be the approximate focal length for this diverging lens. And that's probably about as close as I'm going to be able to get with the technology that we've got here today. So that pretty much wraps up Lab 1-4A, and we'll see how we do on the rest of these labs in the lens chapter. Okay, have a good day. We'll see you next time.